Alright, so in this video we're going to start talking about the chain rule. And the chain rule pretty much tells us a general way of finding the derivative of a composition of functions. So what's a composition of functions? Well, it's basically if you have a function inside of another function. So here we have f of g of x. Alright, so f of x and g of x are both functions, and we've been talking a lot about stuff like that. But remember, from pre-calculus, you can also take a function and just kind of stick it inside of another function, and you'll have a composition. So here, the function g of x is inside of the function f. Or in other words, g of x is being used as input to the function f here. So that's kind of what a composition of functions is. So what we're going to do here is, in this video, we're just going to kind of talk about it informally. We'll see two simple examples of kind of what goes on with the chain rule, and then in the next couple of videos we'll develop this a little more formally. So we'll come back to the general definition there, but for now let's say we have simple examples. Let's start out with f of x equals 3x plus 5 and g of x equals x squared minus 1. Alright, so let's say we want to find the derivative of the composition f of g of x. So we have f of g of x, and let's say we want to find the derivative of that. So we haven't said what the chain rule is, so we can't use it, but before we do that, let's just go ahead and do this directly. Alright, so let's just do it directly first. So what is f of g of x? Okay, no derivatives yet, so just find f of g of x. So if f of x is 3x plus 5, then f of g of x is going to be 3 times g of x, and then plus 5. Okay, so remember the rule for f says whatever is inside the parentheses here, multiply that by 3 and then add 5. So in this case, x is inside the parentheses. And then down here, g of x is inside these parentheses here. Okay, so we're going to take g of x, multiply it by 3, and then add 5. So anyway, what is this? Well, g of x is x squared minus 1, right? So this is just 3 times the quantity, x squared minus 1, and then plus 5 is still floating around out there. So if we distribute the 3, then we have 3x squared minus 3 plus 5. Simplify that, and we get 3x squared plus 2. Okay, so this is f of g of x. Okay, and now we can just find the derivative of that directly, right? That's not too complicated. So let's just go ahead and do that. We're going to have DFDX of f of g of x equals what? So we're taking a derivative of 3x squared plus 2. So the derivative of 3x squared is going to be 3 times 2x, right? And then plus 2 is just a constant, so the derivative of that is 0, so there's nothing there. So then this is just 6x. Okay. So that's the derivative of this composition function here. So how do we go about doing something like this with the chain rule? Okay, so here we didn't use the chain rule at all, right? We just found this directly. And that's fine for simple functions like this. It might be better to just do it directly if you have simple functions like this, but of course you know that in general you can have really complicated, extremely nasty functions, and then doing it directly like this might not always be the best idea. And then you'll want to use the chain rule. So let's just kind of go ahead and talk about that really informally. So we'll leave all this stuff here, but let's section it off like this. All right, and let's go ahead and do this. Let's come up here, and we'll put a little box up here, and we'll put another one over here, and then another one over here. Okay, so what I want to do is, in this box I want to put x. Okay, so here's x, and then what's going to happen is, what do we have over here? We had f of g of x, so we started with x, and then g happened first. Alright, and then we had g of x, and then f happened to that, and then we had f of g of x. So start with x, then apply g, and then apply f. Okay, so we're going to start with x, and then we apply g. Okay. So all we're doing here is just drawing a picture of what's going on the other side. So this is g. Okay, so that's going to take this to g of x. All right. And what happened next, once we had g of x, we applied f to that, right? So then we do f of g of x. So then we have another arrow over here going to this box. And this is f. Okay, so this f is going to take g of x over here to f of g of x. All right, so this is just kind of a little picture of what was going on the other side over here. So start with x, apply g to it, get g of x, then apply f to that to get f of g of x. So what are we doing with this? Well, now what we're going to do is, let's say this, or let's rewrite g of x over here. So g of x, we know from over here, is x squared minus 1. Okay. Now let's come over here and write f of g of x. So f of g of x, now what I want to do here is, instead of f of g of x, I want to write f of g. So we're going to sweep some details under the rug here, and that's fine because we're just talking about this a little bit informally for now, so we don't want to worry about some of the technical details. But instead of f of g of x, let's just say f of g. Okay, so you know, f is just going to take g over here to f of g. So we're going to ignore the parentheses x over here. So f of g, what is f of g? Well, f of x is 3x plus 5. Okay, so in other words, f of a thing is 3 times that thing plus 5. So f of g is 3 times g plus 5. Okay. Now what we're going to do is start taking derivatives. So g of x is x squared minus 1. So what's dg dx? Well, dg dx, remember, that just means the derivative of g with respect to x. Okay, and if g of x is x squared minus 1, let's zoom in a little bit here. If g of x is x squared minus 1, then dg dx is just going to be 2x, right? The derivative of x squared is 2x, and then minus 1 is just a constant, so its derivative is 0. All right, so now what about over here? Here, f is a function of g, okay? So we can sort of treat g as a variable. Now, really, yeah, g is another function, right? But remember, we're sweeping that detail under the rug here, and we're just going to treat g as a variable over here. So let's find df dg. In other words, the derivative of f with respect to g, okay? So f of g is 3 times g plus 5. So what's df dg? Well, if we take a derivative of this with respect to g, that's just going to give us 3, right? If that confuses you, because it's kind of weird with the g, so if you're not really used to that or if you don't like it, let's just come back over here real quick. And f of x is 3x plus 5, right? So what's the derivative of that with respect to x? Well, that's just 3, right? So that's, you know, we're more comfortable with the x notation, we're used to that. F of x is 3x plus 5, so df dx is just 3. Well, we're actually doing the exact same thing over here, but instead of x, we're just using g as the variable, all right? So the exact same thing is happening, but g is the variable instead. And again, yes, g is actually a function over here, but we're just sweeping that detail under the rug. Let's zoom out a little bit here. Okay, so now we have dg dx and df dg, but what about df dx? What does that equal? All right. Now again, we're sweeping some details under the rug here because when we say df dx, we're kind of hiding the fact that f is actually a function of g. All right. So here, f is a function of g, right? F of g equals 3g plus 5, and then g is a function of x. So f is a function of g is a function of x. So basically, f is also a function of x. But you have to go through, if you start at f, you have to go through g, so to speak, to get to x. But because f is a function of g, and g is a function of x, you can still take a derivative of f with respect to x. And the chain rule tells us how to find that, okay? So let's go ahead and see what this would be. Well, actually, we know what this is, right? df dx, we found that over here. So df dx, this is a shorthand way of writing this. So if we say ddx of f of g of x, that's the same thing as saying df dx, all right? And again, df dx is kind of a shorthand notation and a little bit dangerous because it hides the fact that f is a function of g. But when you use this kind of notation, you sort of already know. Let me write that a little bit bigger. DFDX equals what? Well, we know it equals 6x, right? And 6x, well, here we have a 2x and a 3, and do those look familiar? Yeah, we had those over here, right? Here's a 3 and here's a 2x. So we know from earlier that DFDX is 6x, but it's 3 times 2x, right? So we see that here, 3 times 2x. And what are these guys, 3 and 2x? Well, 3 is DFDG, okay? 3 is DFDG. And then multiplied by 2x, 2x is DGDX. Okay, so what actually just happened here? Well, here DFDX equals 6x, which is 3 times 2x, which we saw over here is DFDG times DGDX. So in other words, DFDX equals DFDG times DGDX. And this is pretty much what the chain rule says in this kind of notation here. Let me write that a little more clearly. That's a D down there. DFDX equals DFDG times DGDX. So this is one way of expressing the chain rule. And it is pretty important, but let's just talk about some of the smaller details here. So this notation works out pretty nicely, but it's also a little bit dangerous. You got to be very careful, because you might look at this and think, oh, okay, DFDG times DGDX, well, I could just cancel the DGs, and I'm just left with DFDX. Notationally, it looks like it does that, but that's not really what's happening, because, you know, if you think about it, nothing ever really canceled in this process here, right? And DF, DX, and DG, they don't really represent real numbers. Okay, they represent what are called infinitesimals, which are like infinitely small numbers, which sounds kind of weird, but if you think about infinity, you know, this symbol doesn't represent a real number, right? It represents a quantity that's infinitely large. Okay, that's not a real number, it's just something infinitely large. Well, similarly, DF and DX and DG, those represent quantities that are infinitely small. Okay, so it's pretty much the same concept as this infinity symbol, but instead of infinitely large, these represent something that's infinitely small. Therefore, they're not really real numbers. Well, they're not real numbers at all, so we can't treat them as such. So this cancellation thing isn't really what happens here, but that's just a technical detail. It is important to point out, though. But notationally, it is kind of nice because, you know, you look at this and you think, okay, if they were real numbers, that's what should happen, and the notation is nice like that. Now, unfortunately, this notation isn't very illuminating because this is kind of weird. You know, DFDX, that's DFDG times DGDX, and, you know, this kind of hides the fact, like we said a couple times, this hides the fact that f is a function of g. So we can also express this using this kind of notation. If we go back over here, we can use this kind of notation. So let's go ahead and rewrite this with that kind of notation. So that's going to be ddx of f of g of x. All right, and what that's going to say is the derivative of that is f primed of g of x times g primed of x. Okay, and this is pretty much the chain rule in its most useful form. I think so anyway. I think this bottom form down here is much more useful than this up here. So there are a couple different ways of thinking about it. We've already talked about one, you know, dfdg times dgdx. So this is the derivative of f with respect to g. Okay, so you're thinking of f as a function of g, and you take a derivative of f with respect to g. That's one way of thinking about it. That's not really the way I like to think about it, but I just did it this way because it's the simplest way to introduce it. But another way to think about it is if we look at this, what's happening here? ddx of f of g of x, that's f primed of g of x times g primed of x. In other words, it's the derivative of the big guy evaluated at the little guy and then multiplied by the derivative of the little guy. Okay? So what's the big guy, what's the little guy? Well, f is the big guy because it's on the outside, right? F of g of x. So f is the outside function, g is the inside function. So f is bigger, so to speak, than g is. So f is the big guy, g is the little guy. So chain rule says if you want to take a derivative of a composite function like this, that's going to be the derivative of the big guy evaluated at the little guy multiplied by the derivative of the little guy. So it's a slightly different way of thinking about this same thing here. Here we said derivative of f with respect to g, but here we're saying just find the derivative of f with respect to x, but then instead of evaluating it at x, just evaluate it at the little guy at g of x. So I know this all sounds probably kind of goofy and confusing, but let's see another example, and we'll think of it like this here, f prime to g of x. This isn't really going to work with this example because here f of x is 3x plus 5, so the derivative of f of x is just 3, okay, it's just a constant, so there's really no difference in these two lines of thought here because f is just a linear function. But if we have a more complicated function for f, then we can think about it like this. So let's go ahead and do that. And this down here, so I guess this is worth putting a different colored box around. Let's put a blue cloud around that. Blue cloud. Awesome. Okay, so the chain rule says ddx of f of g of x equals derivative of the big guy evaluated at the little guy multiplied by the derivative of the little guy. All right, so let's do another simple example with that. And we're going to use the chain rule, and we're also going to evaluate it directly, just so we can see that the chain rule does in fact work. So let's go ahead and do that. So we'll erase all this stuff over here, erase this other notation down here. All right, so let's use a different f and a different g now. Okay. Of course, this is the chain rule in general, so for any f and for any g, as long as the derivatives exist. So remember, if the derivatives don't exist, this doesn't even make sense to talk about. But anyway, let's say we have f of x equals, oh, I don't know, let's just say x squared, just to keep things simple. And then let's say g of x is 2x minus 3. Okay, so if we want to do f of g of x, what's that? So we want to find the derivative of the composite function f of g of x. So first let's do it directly, just like we did at the beginning of the video with the other functions. So if we do it directly, what do we have? Well, f of x is x squared, okay? So f of g of x is just g of x squared, all right? And g of x squared is going to be 2x minus 3 quantity squared. Wish I'd chosen something simpler, but it doesn't really matter, I guess. So g of x squared is 2x minus 3 quantity squared. So if we want to square that, basically we're just foiling, right? 2x minus 3 times 2x minus 3. So when we FOIL, first gives us 2x times 2x is 4x squared, outer minus 6x, inner minus another 6x, so minus 12x, and then last is minus 3 times minus 3, which is plus 9. Okay, so this is f of g of x. Okay, this is what f of g of x equals. Oh, good lord. Okay, so f of g of x is 4x squared minus 12x plus 9. So now we can just find a derivative of that directly. Okay, so if we want to find a derivative directly, let's go ahead and come up here. So we'll write it again. F of g of x equals, what was it, 4x squared minus 12x plus 9. Okay, so if we want to take a derivative, then ddx of f of g of x equals what? Well, 4x squared, the derivative of that is going to be 4 times 2x. Okay, and then second term is going to be minus 12x, so the derivative of that is just minus 12. And then plus 9 is just a constant, so its derivative is 0. So we could say plus 0, but there's no point in doing that. So anyway, this simplifies to 8x minus 12. All right? So here, the derivative of the composite function f of g of x is 8x minus 12. So we found that directly. And notice, it was a little bit of work here. We had to substitute that in, FOIL it, simplify, et cetera, and then do the derivative. But let's go ahead and do it again with the chain rule now. Okay, now that we have kind of talked about what this chain rule is, let's just go ahead and use it now. So just to verify that we'll get the same thing. So the chain rule says DDX of f of g of x is going to be f primed of g of x times g primed of x. Okay, so section this off. Okay, so in order to use this chain rule, we have to find the derivative of f and the derivative of g. Okay, and that's good because f and g by themselves are simpler than the composite function f of g of x, right? Now, finding the derivative of this wasn't really too bad. It wasn't very complicated compared to some of the other examples we've seen. But anyway, these are still simpler by themselves. So what is f primed of x? Well, f primed of x is just 2x, right? Because f of x is x squared, so f primed of x is 2x. But we don't want f primed of x, we want f primed of g of x. So what's f primed of g of x? Well, if f primed of x is 2x, then f primed of g of x is just 2g of x. Okay? F primed of a thing is 2 times that thing. F primed of g of x is 2 times g of x. All right? And yeah, we have to simplify that a little more and expand it, but we'll do that down here. Anyways, what's g primed of x? G primed of x equals, well, g of x is 2x minus 3, so g primed of x is just 2. Okay? So now let's take these and put these down here. So ddx of f of g of x equals f primed of g of x times g primed of x. And f primed of g of x is 2g of x. Okay? So this is 2g of x. And then multiplied by g primed of x, which we just found is 2. All right? So now we're going to simplify this. So 2 times g of x and then times another 2. So 2 times 2 is 4. And then we're multiplying by g of x. But what's g of x? It's 2x minus 3. Okay, so we have 4 times g of x, but remember g of x is just 2x minus 3. So this is 4 times the quantity, 2x minus 3. And then when we distribute the 4, we get 4 times 2x is 8x. 4 times negative 3 is minus 12. And we end up with 8x minus 12, which is the exact same thing that we had up here when we did it directly. So this is just kind of a verification that the chain rule works. In the next video, we'll do kind of an informal proof that's actually a flawed proof. There's something wrong with it, but it's good to see that before we see the actual correct proof in the video after that. So that's sort of a informal, semi-intuitive introduction to what the chain rule is.